Can you hear me better now? Okay. Right, okay, so I'm going to tell you about, just to shorten the title, the ETH as a matrix model. And this is some work that will appear soon with my student David Kolschmeyer and with Bauer Mukhamajanov and with Julian Sonner. Oh, you hear some feedback, or? So, can you hear me, or? Okay. Okay, so with these people. And so the idea is to put the ETH, the eigenstate thermalization hypothesis, which is some kind of random ansatz for the matrix elements of light operators between heavy microstates, into the same framework as things like the SSS, the Sad-Shanker-Stanford matrix model for JT gravity. And in fact, the example I'm going to discuss this in is the quantum mechanics dual to JT gravity with propagating matter. Okay, so one might have thought that this relation between matrix models and 2D gravity really only applied to theories of 2D gravity without any local molds. I mean, both from the work on matrix models and 2D gravity a long time ago, as well as the more recent work related to JT gravity. But here we'll see that with a more complicated kind of matrix model, you can describe things which have propagating matter in the bulk. Okay, so that's just the description of the title, basically. And first, I'll give some kind of introduction, and then describe how we can think of the ETH as a matrix model. That's kind of that's the title of the talk. And then we'll go through this example of JT gravity coupled to matter. And here the matter is just going to be a scalar field. And we'll give a geometric picture for what this matrix model is doing, kind of extending the SSS matrix model. But this matrix model will be more complicated, and there'll be many kind of loop diagrams and divergences to discuss, and some particular regulator related to what's called Q-deformed JT gravity. And then at the end, I'll summarize and discuss some future directions. So I hope in this talk there'll be something in it for everyone, because it relates to things like thermalization in chaos through the ETH, and also to matrix models and low D gravity, and even integrability will make some important appearance, because the matrix model would otherwise turns out to be integrable. And it's also related to the conformal bootstraps. So we'll try to explain how all these topics get connected in this business. Okay, so, oops. Yeah, these don't fit very well on top here. Okay. So the goal, to start out from this point of view of the ETH, the goal is to imagine that we have a theory where we know the endpoint functions of light operators. So imagine that we know and you could replace the word light by simple, or so I have in mind something, when I say a light operator, I have in mind that we have a CFD, and light means, dimensions of order 1, not some operators with very large dimension whose dual, if it was in the ADS CFT context, would be a black hole microstate, or if it was some other kind of system that was not particularly holographic, a not light operator would be something which, if you thought about it as a state in radial quantization, would look like a typical thermal microstate with the big degeneracy. So we imagine that we know how the light operators work, so we know maybe the correlation functions of the light operators in the vacuum, and also we can imagine we know the endpoint functions of the light operators in thermal states. So in other words, the low energy, the correlation functions of simple operators in the thermal ensemble. That's kind of the data that the ETH starts with. And if you wanted to compute it from the microscopic theory, again, we can imagine we have a CFT on a cylinder, so it's compact space, so there's a discrete spectrum. So this is, say, SD minus 1 times time. And if we put here, so let's suppose we put here some high energy microstate, and here's some other high energy microstate. And then we could put a light operator in the middle. This thing is the 3-point function of our light operator O between these two heavy microstates. So this is the data that we could write as like F light heavy, heavy prime. And if you knew these, which is the matrix elements of our simple operator of interest between these high energy microstates, then of course you could compute all of the correlators. So if I wanted to compute the thermal correlator of like, you know, O of 0, O of t, I would just write it by the definition, right? It's, you know, let's say I'm in the canonical ensemble, it would be trace e to the minus beta h, O of 0, and O of t. And if I know these matrix elements, I can compute this thing by putting a complete basis of states here, right? So this is the same as the sum over energy eigenstates, e to the minus beta ei, O ij. And then because I evolve this in time, I get some, you know, the usual factor e to the it, ej minus the I, oj I, right? So the topic of discussion today is going to be these objects. And so the ETH, oops, so of course so just to say something obvious, kind of the number of states here is very large. So if we're talking about the thermal system, it has a non-zero entropy. So the number of states in this sum, this, you know, the number of states that this index ranges over is e to the s, where s is whatever the thermal entropy is. That's relevant for this particular question. So there's an enormous number of these states. So if you know the data like this, it's quite a sparse data, right? You know, there are several different light operators, and you know they're low point functions. That's not e to the s amount of data. So there can't be unique OIJs which give a given data, or in other words, given just the correlator data, you couldn't figure out what all the OIJs are exactly. Moreover, we wouldn't expect to be able to compute these in any specific theory in a reasonable way because it's e to the s numbers. So even if it was easy to compute one, which it's not, it will take you e to the s time. So it's not possible to compute these directly. But just like in the study of chaotic Hamiltonians, even going back to Wigner in the context of nuclear physics, if you have a very strongly coupled system and you don't know how to solve it, you might treat the Hamiltonian as effectively random. And so the idea of the ETH is exactly that. It's that, and this goes back to work of Deutsch and Schrednicke. So the idea is that these numbers, OIJ, are pseudo-random. And one writes a particular ansatz for those numbers. Now, when we say the numbers are pseudo-random, there are kind of two ways that we could think about what ensemble what is the meaning of an ensemble. Before I write the formula, let me try to explain what it would mean to say that they're random, because of course in a specific theory, there are specific numbers. So the usual meaning, I think, that is in the original papers on the ETH, is that, well, there are many microstates. So if we look at a particular microcanonical band, that is a range of energies where the physics doesn't change very much between these states, and if you kind of pick the state, the exact state you're talking about in that band at random, then you'll generate an ensemble of these numbers because of the randomness of which level ij in the band you actually discussed. Okay, so there's sort of ensemble of picking specific microstates. And I think that's the sense in which people usually thought of this as an ensemble. But there's also another ensemble that could be discussed here, which is if you measured or knew the correlators that I was just discussing, that is correlators of low point functions of some light operators, that's the specific data. And you could ask, what's the maximum entropy ensemble of these numbers consistent with that data? So in other words, this is a bunch of numbers. In principle, they're constrained by the data through formulas like that. And you could say, all I know is the left-hand side. What's the most generic thing I could have on the right? And that also defines an ensemble. So we could also say that we have a kind of maximum ignorance ensemble. And I think the real moral of the ETH in the most generalized sense is the conjecture that these two ensembles are the same ensemble. In other words, that the sort of pseudo-random statistics of this are the same as what you would get from a maximum entropy ensemble consistent with the low energy data. That's really the moral of the ETH, okay? And that more general statement encompasses many generalizations of the ETH, which we'll discuss today, that are kind of go far beyond the Gaussian ansatz originally written down by Schrodnicki. Okay, so that's the context of the ETH. And oops, yeah.
Okay, sorry. So when you talk about the ensemble of picking specific microstates, this is the idea of Wigner's sort of nuclear physics idea that they're in a small band, we don't know where they are, so we're going to say they're random.
Yeah, I would say Wigner also had this understanding.
Right. So the maximum ignorance ensemble, on the other hand, you're saying we know everything about the left-hand side. I want to deconvolve that integral, basically, and see what distribution I get.
Right.
So the final claim was they are equivalent.
Well, I think there's a sort of the conjecture of the ETH is that they're equivalent, and that's going to be the assumption here. I think sometimes people ask a question like, does the system obey or not obey the ETH, as if it's a binary question rather than like a very specific formula that might have corrections and so on. So I would say if these two ensembles are the same, we might say yes to the binary question, but of course it won't be literally the ensemble written in the first paper by Schrodnicki. There are many corrections. So this is the more, equivalence of these is more general.
Okay, thank you.
Are both of these definitions kind of make sense at large S?
Yeah, they make sense at large S. I mean, I think in principle the second thing makes sense at finite S, but in the sense like
do you know that correlator exactly at all t? Or
well, right, you have to say exactly what you mean at finite S, but yeah, like if I have a specific finite, if I know I have 20 operators that I know about, and I know they're up to 100-point functions to accuracy, whatever, then in S is fine, like. So in that sense, this is a little bit more, Then of course at finite S, it would not be the case that these will be, I mean, this is not really well posed at finite S, right? Okay, and today I'm going to focus on holographic theories. So that the thermal ensemble will look like what we might call thermal mean field theory. That is a theory where the correlator is factorized to the 1 and 2 point functions plus 1 over C corrections. So that's going to be the context today, but I think the story is more general, but that's what we will discuss today. Now, sorry. Yeah, my glasses are very lightweight, so they don't easily sit there. Okay, is this the rest? Okay. Uh-huh. Right, so maybe to I don't want to, before I totally jump into it, maybe I'll mention a few questions to keep in mind. But don't ask me the question now because the talk is supposed to be kind of partial answer to these questions, but these are maybe some of the questions to keep in mind. And the moral of the story is going to be that the ensemble that describes these matrices turns out to look like a matrix model. And this matrix model has many beautiful properties. So we'll see a lot of things come out of this story. And maybe some questions to keep in mind are, and I won't answer all of these today, but I'll say some words about them. So does any gravity effective theory lead to a good ensemble of this type? Or could there be some, effective theories that lead to something that makes no sense here? Or what do you have to discuss to see what some theories have UV completions and others don't? Another question that I will talk a lot about is how non-Gaussian is the ensemble. So if you're familiar with the ETH, the original or conventional ETH is a Gaussian ansatz. So how non-Gaussian is the full story with all the corrections. How does the sum over topologies work? So because I'm going to discuss how it looks like a matrix model, there will be a genus expansion like in the SSS matrix model, and we can ask how does it work, and this will also sum over topologies, so I'll discuss that. And another question to keep in mind, and this I also won't really answer, but I'll say something about it, is how does the CFT, like OPE, determine the thermal correlators? So the way I presented this so far is kind of a backwards direction. It's like you already know the thermal correlators. Maybe you have a theory dual to ADS. You read them off as the correlators of fields on the gravity side and ADS Schwarzschild. That's a kind of input. And from the input, we're going to construct this ensemble of the matrix elements. But could you go the other way? So if I know something about the theory, can I use this methodology to learn what the thermal correlators would be, for example? And I'll say something about that eventually. And maybe just so that we see where we're going, the answer is going to look something like this. Imagine we wanted to compute thermal correlator of a bunch of these operators O, evolved in time. I'm just suppressing the arguments, so we imagine that a bunch of different times. Then what this is going to be equal to, in the sense of the ensemble average will be equal to, is some kind of integral over the matrix O and the Hamiltonian. So it's going to be a two-matrix model at least. If there are other operators, there'll be even more matrices. And then you will insert into it the definition of this in quantum mechanics. So this is like the SSS story, an integral over matrices that live in the Hilbert space. Right, this is the Hamiltonian, it acts on the states and so on. So this will be, trace, e to the minus beta h, O, and et cetera. And I evolve these in time using h as a matrix. So this is an expression I can evaluate if I know the specific matrix h and O. That's the formula from there. But now this is going to be integrated in some ensemble, which will look like the trace of some potential, which is a function of h and O. And it will be important that you end up with a single trace potential. That's not totally obvious. Like from this abstract notion, you'll get some ensemble of matrices, but it's not clear that you would get single trace. It being single trace is really the hallmark of locality in the bulk, in a way that we'll come to see. That's maybe not too surprising, like from the point of view of matrix models in 2D gravity, right? But we'll come to it later. A question?
Sorry, I misunderstood your notation. Why are you integrating over O? What is O?
O is the operator. So
Yeah.
we're going to treat O and H as random matrices.
Oh, so the O's on the left-hand side are sort of symbols for what an operator could be? They're not actual operators?
We could say this is the average of this thing in this ensemble of theories, where the ensemble is the one defined by an ansatz that I'm going to write in a second. But I'm going to, explain it more. But this is a matrix. This is supposed to be a matrix model expression. So this is analogous to the SSS formula that average over the ensemble of z of beta is given by integral, so
Right.
maybe I should write it to remind. Average over the ensemble is integral over ensemble of matrices, trace e to the minus beta h. And then there's a matrix which looks like trace of some potential that we might call the SSS potential. And being a little schematic, they're double-scaled models because the spectral range is infinite. That's true here too.
So now we're adding in.
So this is really like a limit in the space of potentials, but I'll explain.
So we're doing that, but we're also letting the operators fluctuate in this ensemble.
Right.
But somehow the kind of operator, the symbols O on the left-hand side represent like what type of operator or something like that?
Yeah. Yeah, well, if we were in a CFT, O would be something that's supposed to have a specific scaling dimension. But it's like an ensemble of things that don't quite obey all of the axioms or something, and then we integrate over it. I'll try to get into, if I have time, some of the point of that. Okay, so I think now I should write the ETH ansatz on the board, and we'll see how it looks very much like a matrix model. Somehow people, I think, didn't think about it as a matrix model, but they could have. And, oops! Okay. Right. Okay. Right, so the ETH is usually written in this way. I and J are my states of the Hamiltonian, so it's some state. And then we get here the expectation value of the operator in the microcanonical ensemble with energy, say, EI, delta ij. So this is like a classical expectation value, which depends smoothly on the energy. This is just what reproduces the one-point functions. That part's not very exciting. And then the more interesting term is this one, which is usually written as a function of the average energy and the energy difference. And then there's the kinematical factor of e to the minus s, where s is the thermal entropy. And then there's some matrix elements, Rij, which look like a random matrix. And again, when we say this is equal, we mean in the sense that you made an ensemble by thinking about picking the level, the specific level at random, or in the sense of the maximum ignorance ensemble compatible with the light data if you didn't know what the system was, but you only knew something about it. That's the sense in which we get a random matrix here. And the random matrix R is supposed to be normalized so that its variance is 1, and expectation value is 0. So this is the conventional ETH. So it's Gaussian in the sense that this thing looks like a Gaussian random matrix, or only the Gaussian moment has been specified, or something like that. And this is enough to correctly reproduce the 1 and the 2-point functions to the leading order in an e to the s expansion, or rather e to the minus s expansion. So if I evaluate the 1-point function, obviously this thing clicks, and this is some tiny fluctuation suppressed by e to the minus s over 2, so it doesn't affect the leading answer. But if we compute the 2-point function, this term is important. So if we would compute our O of 0, O of t correlator, let's say in the microcanonical ensemble at energy E, that makes it a little easier. You can, of course, go to the canonical ensemble if you want. There's an overall factor of E minus S, which is the normalization of the trace. S is now the microcanonical entropy. And then there's a double sum over the levels in the microcanonical window. We get this function squared. Let's suppose this term is 0 for simplicity, or well, I'll write it at the end, but let's focus on this piece first. We have this average energy and the energy difference. We get it squared. We have an e to the minus s, and it's really, yeah. Then we have e to the minus s from two of these factors. And then we have the kinematic pieces from evolving the operator in time, like that. And then we get the random matrix in this pattern. And so if Rij is a Hermitian matrix, then this is one of the things squared, which is supposed to be this average. And R better be a Hermitian matrix because O is a Hermitian operator. So the ensemble average of this piece is just 1. Basically, and then if we had this term, we would just get O in the microcanonical guy squared, of course. And the factors of e to the s cancel out because there are two factors of e to the minus s, and there's a double sum over e to the s levels. So at the end of the day, the interesting piece here, the kind of connected two-point function, we can write it as an integral over frequency, where the frequency is the energy difference, e to the I omega t. And so we see that the function f is the square root of the Fourier transform of the microcanonical two-point function, or the thermal two-point function. Okay, so so that's the usual ETH. And then there are many different regimes where one could be discussing this. So maybe to clarify something about it, sometimes in some works focus on a very long time regime where one sees, the level repulsion between energy levels because of random matrix statistics for the Hamiltonian. You only focus on a few levels ij in this story, and people have argued for random matrix statistics of the Rij in that context. But that's associated with very tiny energy difference omega of order e to the minus s in extremely long time scales. So that sort of is interesting, but in that regime, this function f is not important because you basically evaluate it at one value, so it drops out. The function f is really important during thermalization, right? That's when the two-point function is like changing non-trivially and not incredibly small. And so in order to make contact with thermalization in the function f, you need the energy differences to be order 1 numbers of order, the inverse of the thermalization times. And today I'm going to write an ansatz that kind of works in the entire range. So the sort of generalized ETH matrix model or whatever, it really works on all time scales between two limits. So on the one hand, it would break down so it works for time scales t that are much greater than if there exists a UV free theory. So if I had a k-local or a local model or a lattice model or a free theory at very short distance, this matrix ensemble that I'm going to discuss won't apply in the regime when you see the underlying nearly free or weakly coupled dynamics. That would happen at very short time scales. If our theory is actually intrinsically a CFT, then there might not be such a time scale, right? Like in n equals 4 super Yang-Mills, there isn't any time scale short enough where it looks free because it's a CFT all the way to the UV. But if we had a theory that looked free in the UV, then this wouldn't apply at very short times. And it also won't apply at time scales that are so long that you have to resum the genus expansion in the language of the SSS story. So, it doesn't apply to like doubly like timescales of order e to the s, okay? But in between, I think we can get everything from the kind of matrix model that I will describe, and that certainly could be the goal, or should be the goal. A question? Okay. Now, I didn't mention the scrambling time in this discussion, and that's because to discuss the scrambling, we need to go to the 4-point function. We can't see it in the 2-point function, and so that's what we're going to go to next. And that's going to bring in non-Gaussianities. And so there has been discussion of non-Gaussian corrections to the ETH. By the way, I have no idea what time it is. Is there a clock somewhere? Okay, good. Yeah. So there's been discussion of non-Gaussian corrections to the ETH. One place where it's clear that that will have to be there is if there are connected thermal higher point functions, right? If there's a thermal 3-point function, that's clearly not going to come out of this. The data isn't in this, right? And there's a nice paper by Foini and Krachan which starts to set up an generalized ETH, which can include non-Gaussianities. But something that is true and is often emphasized is that from the point of view of this formula, the non-Gaussianities are further suppressed by factors of e to the minus s over 2, but in such a way that just the same way that this is suppressed with respect to this doesn't mean that at the end of the day this term is smaller than this term. They're not. So in that sense, they're not small non-Gaussianities. And we'll see in a second when we rewrite it in terms of a matrix model that you would never think of it as a Gaussian matrix model. Right? In the language of matrix models, it's just a non-Gaussian potential, and we'll see how it works. Okay. Great. So this thing just cries out to be described as a matrix model. It looks like a Gaussian matrix model, right? So looks like we took a Gaussian matrix model with two matrices, H and O, and we just chose to diagonalize the matrix H and rewrite it in that eigenbasis of H. Okay, so this thing just corresponds to an ensemble for H and O. Well, the ensemble for H is not written explicitly here because in this formula, it's assumed that somebody else told you the energy levels. So it's kind of like you first pick H and then you're going to pick O. It's, of course, much more natural to treat them on the same footing. After all, the Hamiltonian is the integral of the stress energy tensor, and the stress energy tensor is some operator like any other operator. So it's not natural to, of course, it's a very important operator, but it shouldn't be fundamentally distinguished in that sense. But anyway, we could imagine first picking H, and then we pick O with a model which has some potential for just H. That's kind of the part that picked the spectrum, which is similar to SSS, but maybe in some other context, it will be a different function. And then there'll be a piece that's a function of H and O, and if we take this ansatz literally, just this Gaussian thing, it will be Gaussian in O, but a complicated function of H. Okay, so maybe to make it clearer, I'll write this function V. So V is a function of two variables, right? Or of two matrices. And it's this function. We have to write it in a somewhat funny looking way, but in order to see that it's a single trace term, but you'll understand in a second. Okay, so that's the potential. Oh, sorry. I guess I meant the inverse because of the way it's written over there. Okay. So what does this mean? This means if I integrated E and H, integrate out E, these are just delta function, it would just say that I plug H into this function. But I can't just write it in a totally trivial way because the operator order of O and H matters, right? But it's still single trace. Linear combination of single trace things is single trace. So this is the matrix model way of writing the usual ETH. This is just a bookkeeping. but I think it's already kind of a nice way to think about it. Yeah.
I don't understand these delta functions that look like they're between a matrix and a scalar.
Mm-hmm.
If H is a matrix and E is a scalar, how am I supposed to interpret that?
Well, yeah, I mean, it's the formal gadget where if you did the integral over E, you will insert H into the function, the other function as a matrix. Oh, I mean, we could say it a different way. I mean, you know, you could take the function, expand it into power series, and then you plug the matrices into each term in the power series, right? Yeah. It's just another way to write it. Okay. But the point is that anything that looks like, so, I mean, this thing will be equal to the following. We can write it in energy eigenbasis as OIJ, OJI, and then this function of, which is a combined function of EI and EJ. Let me call it G, where G is this function. So when I write it like this, it might not be obvious that it was single trace. This formula is supposed to make it clear that it's single trace. It's single trace because of the way the indices are solved, even though this is a function of both. Because we can power series expand it, and each term separates, right?
G is 1 over F?
Yeah, G is 1 over F because this thing kind of says that if I rescale it, and actually there's a, yeah, so G is 1 over F. That's what this is. There you go. Okay. Right, now, so this is going to fit the ETH in with the SSS picture. Let me remind you how that looks. We could say it in the following way. So right, I mean, the point of the SSS idea is that, you know, on the one hand, there's, you know, the Wigner type of random Hamiltonian, which is expressing the fact that in a chaotic system, the energy levels look random, but it's not that each energy level is a random number, it's that the Hamiltonian matrix elements look random. And so then when you go to eigenvalue basis, you get the Vandermonde, which looks like a product over energy levels, squared, and this leads to level repulsion, which is the hallmark of chaotic systems at the very short, you know, very long times and very small energy differences, and you get that kind of spectrum. What SSS understood was that this kind of, you know, Wigner-like thing is the same as a matrix model that, you know, you can fit together that and the matrix models that related to 2D gravity. And I mean, of course, their work was for the specific case of JT gravity. In JT gravity, there's an additional statement that the range of the spectrum is infinite, so it's a double-scaled limit of a matrix model. So the range of energy is not in some finite range like in a usual tough-scaled matrix model, but between 0 and infinity. So this potential is a kind of limit in the space of potentials. And in JT gravity, the spectral density is given by the sinh of the square root of the energy. And that's, you know, there's a one-to-one correspondence in matrix models with a single Hermitian matrix between the matrix potential and the genus zero density of states. So saying this is tantamount to giving this potential, although the formula is a bit complicated. So I won't write it. They didn't write it actually in the paper, but if we looked on the gravity side, so somehow this matrix model, which you might have first thought had this Wigner kind of picture, just like some bunch of random levels. now gets a beautiful geometric interpretation because the 't Hooft diagrams of the matrix model, if we compute something like trace e to the minus beta h, we fill this thing in with the nest of a 't Hooft diagrams, and in the double scale limit, it builds up the 2D spacetime, just like in the old matrix models. And with this particular choice of potential, you get JT gravity. JT gravity is the theory of 2D gravity, which has the bulk action given by first a term which is just like the Euler density. So this is a purely topological term in 2 dimensions. And then the more interesting term that's characteristic of JT, which looks like this, where phi is some fluctuating field. So this acts as a Lagrange multiplier that just sets the curvature to be constant. So the local geometry is always just empty ADS2, looks locally like ADS2, and the only thing that fluctuates is the boundary of the space. I assume people are pretty familiar with this story here. But in Lorentz signature, you get things like a 2-sided black hole, where you stop the space perhaps at some point that's analogous to the singularity, where maybe phi goes to minus phi naught. Yeah?
I'm sorry to ask these things, but before I kind of got lost too much,
Yeah.
I'm kind of following up probably Matt's question. If you look at this ensemble average of OOO correlator, this on the left side, the top O beta up.
Yes.
And then where is the information about which operators ensemble we consider on the right side? Because it looks like O is integrated, and then I thought you would explain us, but I still didn't get, because O is integrated, right? On the right side expression.
Right, so you integrate the matrix elements of O, and then the quantity that sits there has a specific expectation value, and that's the answer.
But what's the symbol of the O?
It's an integral over O. It's like a matrix model, so it's an integral over O. Just like here, it's an integral over the matrix H.
Yeah, but then where is the information about which O on the left-hand side you want to compute?
Well, I'm not sure what it means, which O. What does that mean?
Oh,
Well, I mean, let's imagine we have a holographic theory in mind.
Yeah.
Which we're going to discuss in a second. So there will be a scalar field coupled to JT gravity, but
Yeah.
scalar field from the bulk point of
Yeah.
view has a specific mass. The O will be that scalar field.
Yeah.
Always. So
Yeah.
that's what O means.
But
But when we say that we have a scalar field in JT gravity, it doesn't tell us the fine-grained matrix elements,
Yeah.
and that's what's being averaged over.
But I thought you're kind of going beyond Gaussianity or something. You have a low energy field, maybe some, correlated different field by field and so on. So you have to specify like.
There might be many fields, so doesn't have to be just one kind of O. There could be some other O's. But
Yeah.
here I just wrote it for one O. So in that formula, it's imagining a theory where I'm interested in only 2 questions, the energy and a particular light operator called O. And I didn't write the formula for any other question. And if you wanted if there was some other light field,
Yeah.
then there will be another operator,
Yeah.
O tilde, and there will be another integral over O tilde. It will be a different matrix. Okay?
Oh, yeah, the right-hand expression have to change.
Yes.
That's all.
So this is a special case where there's just one operator under consideration. But in general, every field in the bulk will get its own operator. Yeah. Oops. Okay. So, right. So that formula is really the main conjecture, except as we just discussed, if there were many fields, or let's say we have 10 light fields, then we will have a 10 matrix model. And it will always be a single trace if the bulk is sort of a local holographic theory. Like in the 1 over C expansion on the gravity side, or the G Newton expansion on the gravity side, we'll get something single trace over there. And once we write a matrix model, we can also discuss the sum over topologies, which was the main point of the SSS story. So in addition to things like the disk, there can be what people call the double trumpet and so on, which are defined because we have this ensemble average. And one can discuss the sum over genera here. And it has some interesting answers which also connect to the gravitational dual of what will be soon JT gravity coupled to matter. Right. Ah, I see, right. And for one matrix models, the way that works goes back to matrix model recursion. And in a sense, what the analogous story here is recursion for multi-matrix models, which I actually don't know was ever developed in the study of matrix models, but it seems that it also works. Okay, let me try to get to some of the actual results here. So the first point I want to make is that the Gaussian ansatz is wrong even for mean field theory. So if we had thermal mean field theory, that means that the correlators are supposed to factorize to the 2-point function. So let's assume the 1-point functions are 0 for simplicity, and if I have the 4-point function, it will be the sum of 4 diagrams. These are like bulk Feynman diagrams or just Wick diagrams of thermal mean field theory, and there will be 3 of them, sorry, sum of 3 Feynman diagrams. But if we would do the computation in this Gaussian ETH, or the Gaussian in the matrix model that was Gaussian in O, we get these 2 diagrams, but we don't get this one. And you can see it directly from this way of writing it by, how you need to contract the indices. Because, here we have something, we have 4 O's, and we have OIJ, OJK, OKL, OLI. And if you want the thing that contracts these 2, you only need to pay the price to make K equals I. But to contract these 2, you need all the indices to be the same. So you pay extra e to the minus 2s. And that contraction here actually corresponds to this diagram with the handle where the lines go like that. And things similar to this were studied by Phil Sod, among others, at some point. But this is not the correct answer for thermal mean field theory. This is some very tiny correction. Thermal mean field theory just gives the answer 0 for this. In the language of matrix models, it's also obvious. If you have a model which is Gaussian in O, the O lines can never cross. So you can't make this because the bulk is made out of the tough diagrams. So you need to add something quartic even to get mean field theory. To put it another way, the Gaussian guy has the scrambling time equal to 0. It's instantly scrambled. The out of time order correlator is just identically 0 even from the beginning. And this is like the ultra late time correction, but that kicks in immediately. That's the only contribution even at t equals 0. So that's not good if you wanted to, really describe the whole theory, and one needs something very non-Gaussian. So in fact, we can understand it in a different way. Mean field theory is a free theory in a certain sense, and so the operator commutator is equal to the identity operator times the causal 2-point function. This is familiar in GFFs, right? Only the identity and double twist operators appear, and there's no singularity in the double twist correlator when going to Lorentz signature, and so they don't contribute to the commutator. This is a constraint, right? This is an equation that should be obeyed by the matrices. If I pick the matrix H and O at random, they will not obey this. So I need to impose this constraint. And it's a Gaussian constraint, and it makes, therefore, the model not Gaussian to impose the Gauss quadratic constraint. And one way to impose this constraint is to take its square and add it to the potential with the coefficient that you will try to dial to infinity. So we add to the matrix potential our V, not just the Gaussian thing, but some coefficient A that we're going to take big, trace of this constraint squared. And in the limit that a goes to infinity, you will impose the constraint or break the model, I suppose. But the constraint squared looks quartic in the matrix O. So it's some kind of quartic two-matrix model. Now, that might make the model very hard to solve because generic multi-matrix models are not solvable. But this kind of matrix model has a special integrability that makes it still work. I see I will not get to answer the more speculative questions because I will not have time. But I'll just try to get to the main lesson. Sorry, I need to take a brief sip of this. Hold on
A quick question. Daniel?
Yep.
The constraint is a matrix constraint, but so if you just impose it as a trace, will it really be imposed by adding a trace term to the?
I think I missed something, so.
I'm saying the constraint. Sorry, can you hear me now?
I
The constraint is a matrix constraint, so if I
Yes.
just add a single trace in the exponent, will that really impose the constraint?
Sure, because it's a positive quantity, right? So, I mean, if I have, this thing is this is a Hermitian matrix. So when I say the constraint, I take this, I write it like this. Now the left-hand side is a Hermitian matrix. And so if I take it square, it's a positive quantity. And so that's why it imposes the vanishing of all matrix elements. But there are infinitely many constraints because this is true for all t. So you have to really impose the integral of the constraints for all parameters, and then you will have imposed all of them.
That constraint is true in mean field theory?
Yeah.
But it's not an exact thing.
Right. It's not an exact thing. It's just for mean field theory. Yeah. Now, I really wanted to discuss something more interesting than mean field theory, namely JT with matter, and that obeys a similar constraint. So for JT coupled to matter, the two-point function, maybe just to put a formula to it, the two-point function was computed, and from that we can deduce what the Gaussian part here, I'll put 2 to mean the Gaussian part. That looks like this. Where in this notation, plus minus means the product over the 4 terms. So if you take that and you plug it in, you'll find the two-point function of JT gravity coupled to matter that's been computed before. And then we can go to the 4-point function. For JT gravity, the cross diagram in the 4-point function, which is like the out-of-time ordered correlator, which was computed by Terriaci, Verlinde, and someone else, sorry. And also other people discussed it, like Zhenbin and others, but many others actually. In any case, if we take the 4-point function and we go to energy basis, just by taking, Fourier and Laplace, Fourier transform of the correlator to go to energy basis, and I strip off the propagators, the end result is the so-called 6J symbol of SL2R. Which is the specific function of these energies. It's some specific special function. So this is different than in mean field theory because it contains the interaction with the Schwarzian or boundary graviton, but it still means that there is a constraint that's being obeyed. It's just a little bit more complicated than this constraint. It basically says that some kind of transform of the product of two O's integrated against not delta functions, but this change the answer. So it's kind of like crossing dressed with the Schwarzian is the constraint. One way of saying it is that the amplitudes, at the level of the amplitudes, they obey the property that if I integrate energies against the six, I think of this as, say, a function of energies, and I integrate this energy against the 6J symbol, evaluated here with those two energies, the total amplitude stays the same, because the total answer is the sum over all of these diagrams, and with equal amplitude. So there's still a constraint, but it's a little more complicated. And when you take this constraint and square it, the interesting quartic term exactly comes from this 6J symbol. So for the JT model, you would expect that this function, again, to write it in a single traceway is kind of complicated, but it's like a, we have OIJ, OJK, OKL, OLI, and then we have a function of the four energies, and this function has one term which is the 6J symbol and one term which is a delta function. So we can write this thing diagrammatically as this plus this minus that. That's what the constraint looks like. Constraint squared looks like this. So that's the specific model. Now, I tricked you a little bit in writing or saying this, because what we know about JT gravity with a scalar are the answers. And the answers are not directly the matrix potential, right? Yeah, okay. So I'll just explain this integrability thing, and then I'll stop. And then I'll say just in words for 2 minutes what the rest of the story would be. So now we have a two matrix model, which is not Gaussian in either matrix anymore, so you have to sum many planar graphs. It has the complexity, at least, of phi to the fourth theory, right? You sum everything. It sounds impossible. And the relation between the matrix potential and the amplitudes might be complicated. The thing that saves the day is that if the matrix potentials are made out of these particular functions that involve just, say, delta functions and 6J symbols, they obey standard integrability type equations. Like if I take two 6J symbols and solve them like this, it's equal to that. And the Baxter equation, that thing is the same as this thing. And so because of that, all of the graphs can be unlaced. And then there's things like with a loop like this, which looks divergent and has to be regulated, and I don't have time to discuss it, but it's basically this up to regularization. Because of rules like that, all of the diagrams unlace to the same thing, so you get very simple functions of energy as the output, just linear combinations of these diagrams are sometimes called chord diagrams. And that's what makes the problem manageable. So that's how you can kind of go back and forth between the matrix potential and the amplitudes. So from the point of view of reproducing just the disk answers, this is the story. So if we wanted to write the generalized ETH for JT gravity coupled to matter, we get this quartic matrix model, and then you will evaluate your amplitudes in it at planar level, and they will agree with the gravity computation. But one can go much further. So you can use the same matrix model to compute the higher genus contributions. The simplest one is the double trumpet. And the matrix model reproduces the determinants of a matter theory on say, the double trumpet. And then there are actually various directions it can go, because there are some divergences in the computation. Also divergences related to the fact that it's a double-scaled model. If we had a not double-scaled matrix model, everything would be finite. But because it's double-scaled, there are various divergences, and they have somewhat different interpretations. And it turns out that there are really distinct models, all of which could be interesting. There is one way of tuning the potential, taking the limit in the space of potentials when you do the double scaling limit, where you get the answers of JT plus matter on the nose. And they have a big divergence as this length goes to 0. And you can see it in the matrix model by having an infinite number of 0 modes of the Hessian of the eigenvalue distribution. So I could explain it to somebody afterward if you're interested. And it looks like at higher genus, the matter determinants are given by something called the Selberg trace formula. So there can be pictures like this, and the matter determinant is related to geodesics that wrap the manifold in different ways. These are reproduced by this matrix model, so it agrees with the Selberg formula. But then there's a different model that's interesting, which we call the Q-deformed matrix model, which connects to the deformed version of these, which appears in the double-scaled SYK model. And even in the Q goes to 1 limit, it gives different answers at higher genus. And in particular, it has some kind of Hagedorn-like spectrum here. So it looks like a string theory, and it has some different behavior there. So I think actually one can really learn something out of these matrix models. It's not just that you already know the answer, and then you just find an ensemble that matches it. Once you understood the ensemble, you can ask these higher genus questions, and you really learn something about the bulk theory that you didn't already know. So I think that's interesting. And there's a very general version of this story that applies for any CFT. If we have a non-holographic theory, we need to introduce a matrix for every operator, not only the primitive ones, but also the multi-twist operators. They each get their own matrix. And crossing is a constraint exactly of this type. Crossing is quadratic in the structure constant. So crossing squared is quartic. And so we can imagine a story where somebody told us the light data, dimensions and 3-point functions of light operators, and then we treat everything with heavy operators as random, including tensors, which are 3-point functions of 3 heavy operators. And then the entire matrix tensor potential looks like all crossing equations squared with a coefficient that one will dial to infinity. If you didn't have the tensor part, you'll just have a matrix model. Then it will be very similar to this, except graded by spin. And instead of having this 6J symbol, you get the 6J symbol for whatever conformal group, whatever is the symmetry group. But once you include the tensors, so in matrices, these always work in the sense that double-scaled matrix models always give you something that looks like gravity. But with tensor models, it's much more delicate, and I think there's something to explore there. So those are kind of the future directions, and thanks for listening.
Questions?
So you were saying these things about double trumpet very quickly at the end.
Yeah.
But I just want to run the following statement that it sounded like you said to see if it's what was in code, was a subset of the things that you said. Story dating back a few years was that if you consider matter field on top of coupled to JT, consider double trumpet, amplitude is divergent.
Yeah.
And then there's the question, what do you make of this? And it sounds like you're saying that you can make sense of this, not with there still being an ensemble dual that produces double trumpet in genus expansion of blah, blah, blah. So there's a well-defined ensemble even if the bulk amplitude diverges, seemingly rendering the bulk you might have wondered if the bulk was an inconsistent theory of gravity based on this divergent amplitude, but you're saying there's a more fundamental structure that still is there. The ensemble, is that?
Yeah, I would agree with that. But the way I would understand it is you really should have regulate the answer. So here we're working backwards. We're starting with gravity answers, so imagine you should regulate the gravity answers. Then you will define your matrix model. Then you could compute the double trumpet. It's finite, and it has the property that in the limit it has the divergence, which matches the gravity divergence.
And your regulator is the double scaled versus finite cut, or?
So if it was a finite cut, you can never get a divergence, but you can also tune There can also be double-scaled guys where the potential decays fast enough that it's still finite and still double-scaled. And those look like modifying the UV in the bulk, especially the ones which are still double-scaled, but the potential just dies. Looks like modifying the UV in the bulk. Whereas if I make it not double-scaled, it also modify the IR, right? Because it has a maximum size black hole. And with those kind of modification, you get something finite. But the question is really, how do you define the model in a sort of Wilsonian way, right? Like you would want to do in the matrix model side the analog of effective field theory on the gravity side. Something similar came up even just studying dynamical end-of-the-world brains, like this paper I had with Ping and David. There, the trumpets already give a divergence. It's a much softer divergence, like rhythmic instead of exponential. But in order to make sense of the theory, we had to say that you kind of add an additional single trace term and take the scaling together in an appropriate way. And where the thing that you want to keep fixed is the IR effective Lagrangian on the gravity side, and not the UV effective Lagrangian. So in pure JT, it's we're doing something that's sort of not what we usually do, which is, it's like we're saying we know the UV Lagrangian of the bulk theory, which worked because it was kind of perturbatively finite. But once you have matter, you really want to fix the IR Lagrangian. So there's still something to be done, I would say, to fully iron that out. But there's, of course, some amplitudes which are perfectly finite. Like if you look at this thing in B basis, B is the length, it's a finite number. Or this is finite in B basis, and so on. So you can see that it matches and the divergences match in a sense.
Okay. Well, one other question. You mentioned that you can imagine incorporating, at least in principle, constraints coming from conformal invariance. What about the R-symmetry constraints as well?
You mean in the supersymmetric theory?
Yeah.
Yeah, so I think the story is completely general. I can explain in 1 second why the 6J symbol appears, which is if let me erase this. So it's always the 6J symbol, so if I have crossing is that, and I take the square, the interesting term is the cross term, and if you think about it, it looks like a tetrahedron. The 6J symbol of a group, by definition, is the thing you get by picking 6 representations and summing over the whole module of the Wigner 3J symbol on each vertex. So that's automatically what you get from crossing squared. So if I, so in other words, when you say you have an R symmetry, it means that you're only going to tell me the primaries of the whole group, and then I'll get the 6J symbol of that group.
All right, if there are no more questions, then let's thank Daniel again.